All right. Okay, let me start. Yeah. So our topic is as shown here, so liberation from biological limitations via physical, cognitive, and perceptual augmentation. So, so this is a list of milestones at the program level. So this is common across all the PMs here. And so our final goal is at the top. So by 2050, we want to develop technologies that transcend the limitations of space, time, and human abilities to realize a society in which everyone with different backgrounds and values can participate in a variety of activities according to their own lifestyle. And then we have a breakdown of this goal into various stages. So, so in the following slides, I'm going to I'll tell you about what kind of role we are going to play across different stages in this project. Okay. Yeah. So yeah. So the so this is the milestone for 2030, and at the program level, we aim to look to realize a society of like remote mutual aid, and so people with disability can participate in social activities, and so so this is still like 8 years ahead, and I believe that what we are going to work on in my current project will have synergy with Minamizawa-san's group. So, so in our part, we are going to develop something we call AI-assisted trusted BMI CA. It's a very long name, but I'll explain this concept more in detail later. Yeah. So, but eventually what we want to achieve is augmentation of human abilities, and especially from the perspective of neuroscience. And so, but by 2025, we want to develop a technology to share ideas directly. So as part of the development of AI-assisted trusted BMI CAs, we want to develop technologies to allow people to communicate directly through their thoughts. So it's basically brain-to-brain communication. And so, but maybe, it's still like a science fiction-like idea, but we want to make a steady progress so that we can speed up the communication among people. And so, but to assess that, we want to make it possible that people can communicate much faster than what we can do currently. And in a nearer goal, we first work on more non-invasive brain recordings, namely EEG. And so in an early stage, we want to be able to sort of create sort of applications and devices that people can use without any surgery, so that they can use ideas or thoughts to control cybernetic avatars, and also to understand their own mental or physical state from such biological signals. All right, so this is a very busy slide, but we want to make progress in two directions. So along the horizontal line, we map technological innovation. So like in an early stage, like in 2023, we want to have much better methods to estimate the mental state, and also like motor and speech intention from brain activities. And then in a later stage, by 2025, we want to augment like physical and cognitive abilities abilities. And also, we consider applications from the perspective of invasive brain-machine interface. And eventually, we want to be able to connect the brain directly to the internet. So that's maybe not completely possible by 2030, but that's the direction we are aiming for. But to make this happen, we will need, we want to make sure that this is ethical and also it makes economical sense. And also, we have to consider, various social norms to gain societal acceptance with this kind of approach. Because when we talk about sort of manipulation of brain activity or reading of thought directly from brain activity, that could provoke a lot of fear in non-experts. So we consider communication with the society is a very important aspect. So that's this vertical axis. So we want to start from gaining trust, and by communicating the contents of our technology, and also open discussion of sort of potential impact to the society. And then we also want to gradually show the sort of usefulness of our approach. And initially, maybe it's not going to be common to put electrodes into healthy people's brain, but in an early phase, we consider application of such technology just in patients who would actually benefit from this kind of approach, right? And so the key word is this AI-assisted trusted BMI-CA. So the AI-assisted part is we apply artificial intelligence to improve all aspects of brain-machine interface. And as I show you here in the graph, there is a trade-off between safety and sort of function. So if we have more invasive recording, we can always get more information. But then it's not easy to do. And so on the other hand, when we record just from a very simple non-invasive EEG, and then the depth of information is very limited. So but we can improve this trade-off by applying deep learning for decoding, and also reinforcement learning or other methods to control avatars. So this is kind of a general overview. So here I'm just showing kind of a setup where we would use a normal EEG setup, but these days, with a lot of data and deep learning, we can improve the decoding performance. And our goal is not to decode all the detailed motor commands, but instead we want to decode high-level intention, so that the intended outcomes are going to be achieved by half AI. So we are thinking about some sort of semi-autonomous system. So we also sort of train robots in AI in simulation, and then we use that policy or the learned strategy to control avatars. But then the important thing is we use a technology called shared autonomy. So basically, we first train an AI that can perform the task autonomously. But then, but this AI also accepts intended action from decoded from the brain activity, so that they are going to be combined. So it's a little bit like Minamizawa-san's experiment where two people manipulate a common object. But in our case, one comes from the brain, the other one comes from AI. So this is our whole team. There are generally 5 research items, and the first one is mainly non-invasive neuroimaging. And the second one is the AI part. They develop various aspects of AI. And then the item 3 is basically invasive neural recording. So they do a primate experiment, and also Professor Yanagisawa records from human brain in patients when they need surgery. And item 4 is for sort of like supporting all aspects of research progress, and especially we built, we discussed like ethical LC implications. And this item 5 is a new one that's starting very recently. And so I cannot say much about this new content yet, but generally we are also, in this group, we are aiming to produce a completely new kind of brain-machine interface, which we call minimally invasive BMI. Okay, so I just give you kind of a brief overview of what we do. So brain assistant team, which is basically like a non-invasive brain-machine interface team, we aim to, we build our own EEG device. So that's, actually, so these days there are a lot of like commercially available like cheap EEG devices, but we are developing a device that can record at like a really like medical quality data, but also it's very easy to use. So we need roughly like 30 seconds to set it up, and eventually like we want to make this into a product that comes out of this project. And also we record EEG and also other sort of biological aspect of walking to understand what's happening in the brain while people are walking. And also we use this kind of information to sort of estimate mental state of the walker. So that's another thing we're doing. And also since with this new EEG device we are developing, we seem to be able to collect a lot of data from everyday activities. So that's also like in the like research studio we visited on Wednesday. We are collecting a huge number of brain-machine interface EEG data. So that's actually the world's biggest data set. So that's so in a way, for this non-invasive part, we are very focusing on the quality of data and the quantity of the data, in the belief that we can make a difference by having such data set. And also in our goals, I mentioned brain-to-brain communication. So eventually, we want to allow people to think to communicate. But of course, it's not easy to do that immediately. So we are doing this in animal experiments, but at the same time, like we are also doing this proof of concept, just using AI. So the image shown in the middle sort of illustrates that kind of translation of between neural networks by finding a shared representation between two AI systems. So it's a little bit similar to unsupervised machine translation, but we want to find methods to translate sort of between different brains. So because everyone, so inside the brain there is some sort of special code, and everyone has the kind of maybe kind of different like brain needs or something, and so we use AI to translate languages specific to individuals. Yeah, and so this is a new development, but so just briefly, so this is not, we don't reveal all the details yet, but we are thinking about like using like ultra thin film electronics to record from like high quality ECOG level signals from without surgery. So that's again like a big goal. Okay, and then also, as I mentioned, we have a team to work on more like ethical, social implications. And in this team, maybe a key project is the one in the middle called this kind of brain tech guidebook. So we have a team of experts, and then to write this guidebook for lay people so that people understand what is currently possible with the existing technologies in neuroscience. So now, maybe with some inspiration from Elon Musk's Neuralink, there's a lot of hype happening in the domain of neuroscience, and so there are a lot of new companies producing sometimes maybe kind of dubious products. So we want to share expert knowledge about how we should approach about this kind of commercial products. And also, we are performing large systematic reviews on like typical claims used in that kind of devices. For example, we have done a systematic review and meta-analysis on the claim that neurofeedback with EEG improves like motor performance. So, and then we have done a systematic review and evaluated whether such claim is trustable or not. So those are also going to be published, and so we are working on 12 such questions. Okay, so those are the kind of general structure of my team, but I think it's probably more interesting to show you the results of some ongoing projects. So the first one is the massive data collection we are doing at our research studio. So as you can see in the picture, we have something we call this kind of brain information sequencer. So we have a high density EEG. I think it's like 190 something channels, and then we record heart rate, and we track eye movements, and we have a stimulator and EMG recorder. So yeah, but so this is meant to collect a lot of data related to EEG-based brain-machine interface, and so we collected currently from like more than 138 participants, and so this data is going to be shared, and it's currently probably one of the biggest data sets on this topic. So we hope that we can involve like a lot of people interested in developing brain-machine interface sort of algorithms and using this data set. And of course, within our project, we share data, and we work on the development of new algorithms, but this is like really useful resource in our team. And also, this is also from Ushiba's team. And so he's developing this sort of wearable portable EEG device with 3 channels, and just over the positions called C1, C2, CZ, I think. Or maybe not, C3, C4 maybe. But the point is, those electrodes are over the like, somatomotor areas. So it's very useful for detecting some well-known signal called SMR. And so the idea is to use this as an interface to control avatars with non-invasive methods. So currently, like we have some demo of sort of walking around inside Google Street View, and also we are working on kind of like gliding in the plateau environment, which is kind of 3D model of the city. And also we have developed a space on Fortnite so that people can practice controlling their brain waves just by playing the game. So this is what's happening. And also for the invasive side, we have several things, but in this team led by Komatsu, she has implanted ECOG electrodes covering one whole hemisphere. So basically, we have almost like a full coverage of the whole brain, and half of the brain, and so that's and the great thing is it's completely implanted, so this animal can move around freely, and then we can. Yeah, I'm not showing the animal, but animal is kind of moving around in a cage, and but at the same time, like we get like a very high temporal resolution data, and so this is this gives us maybe much more resolution compared to non-invasive method. And what we are doing now is so we are using this to send the marmoset monkey to virtual space. So this part is showing the signal coming from ECOG. ECOG is the EEG measured on the surface of the brain, and then we can predict what the monkey wants to do next. So now already the decoding performance is like over 90%, and it's decodable even before the animal makes the movement. So basically, yeah, so we can sort of reproduce the events happening in this virtual environment. So it's actually like quite spooky to look at this image side by side with the actual animal because they're doing the same thing. So yeah, so that's that's our current state. But what we want to do next is we want to this animal to use this avatar to communicate with other animals inside such a virtual environment. So that's still that's kind of a step forward towards think communication. Of course, eventually we want to do this with direct stimulation of the brain, but we also need a little bit more technological development to achieve that. And also in humans, it's harder to get a lot of data from humans because it's possible only from patients who undergo surgery. But yeah, but this the team from Yanagisawa's group has published a paper that shows the image based on the imagination of the patient. So this patient is asked to imagine word, and then this decoding from this human ECOG predicts what kind of category or what kind of semantic contents that the signal corresponds to, and then based on that, you can see when the patient is imagining a face, then the algorithm kind of shows face images. So eventually, what we want to do is we want patients to be able to generate any image they have in mind. So to do that, we are also adding additional things maybe if you're familiar with the method called Big Pi GAN and some sort of GAN image generator, we can combine that to some semantic latent space. So that's the that's what we are working on. Yeah, but today I'm just showing already a published result. But we are making progress, and we have this Yanagisawa's group is also collecting a lot of data from patients, and so that's going to be a very valuable resource for us. Okay, and okay, so this is the concept of brain-to-brain communication. So I'm kind of comparing the brain to encoder-decoder type AI. So so usually when we encode something, for example, image of an apple through eyes, then that becomes the concept, and then we translate that concept into words or image. So maybe we can draw the image, And then we can communicate, again, through the outside of the brain. And then another person can re-encode that information to understand what the other person saw, the other person is saying. So, but we want to directly, we want to sort of connect the latent spaces of the two brains. And so that's also another project happening in our project. So as in the Yanagi-Sara's group's ECOG experiment, it's getting possible to decode the contents of mind just by using a single animal. Or, like, for example, here, we can create a decoder to predict what kind of image animal is looking at. But this has been always done individually. But if we manage to find a common latent space, then we can have, all we need is just to decode from this latent space. So all the latent spaces of the brains will be aligned. And so, so what we want to do is, if we can align latent spaces, then we can sort of extract the idea from one animal and then send that, then translate that sort of pattern to another brain, and then stimulate. Then that way, the concepts can be transferred. So that's the kind of general concept. But right now, we don't have find enough methods to sort of inject that kind of information. But as I said, there are like excellent machine translation algorithms, or like many types of sort of latent space alignment methods. So AI technology is there, and we have the ability to collect data. So if we combine this, we should be able to do this. At least we can establish proof of concept. Yeah, and at least for AI, between two AIs, we know we can already align two things. So here I'm showing like blue neural network trained on images, and another neural network trained on another set of images. But then we can align their latent spaces together, and then through that shared representation, we can translate. So if you input a set of images to one network, then you can reconstruct those images, although they are trained separately. So yeah, that's typical translation. Yeah, but this is, I'm showing this image to kind of so that to help you imagine what it will be like to connect brains. So these twin sisters had connected brains congenitally, and so their thalamus is connected. But they, anecdotally, they report they share experience. So one person can taste what another person is eating, and also one person can see through her sister's eyes. So that kind of experience sharing seems to be possible. Normally this doesn't happen in typical brains, because our brains are all individuals. So in that sense, we always assume consciousness is like private, and we cannot like really share experience. But maybe in this case, biologically, like their brains are connected through like a high bandwidth network, and so if we manage to sort of connect two brains, even through technology, we may be able to reproduce that kind of experience. So that's the inspiration. Okay, yeah, thank you very much.